Consider the primal dual pair of linear programming problems P and D, where A is the matrix 1, 2, minus 1, 1 in the first row, and 0, 1, 1, minus 3 in the second row. B is 2, 1, and C is 1, 3, 0, minus 1. And capital B is the basis 1, 3. We're going to look at two questions. The first is to show that capital B is an optimal basis. And the second question is, if C1 is changed to theta and C2 is changed to gamma, for what values of theta and gamma does capital B remain an optimal basis? So let's look at the first question. To check that B is an optimal basis, we need to check two conditions. That B determines a basic feasible solution, and that Y star satisfying Y star transpose A sub B equals C sub B transpose implies that Y star is feasible to the dual problem. And because Y star satisfies these equations, the only things that we need to check are Y star transpose AJ less than or equal to CJ for all J not in the basis B. So let's check the first condition. So to obtain the basic solution determined by B, we look at this system A is equal to B and set the non-basic variables, in this case they are x2 and x4 to 0. So the system is x1 plus 2x2 minus x3 plus x4 equals 2, and x2 plus x3 minus 3x4 equals 1. And if we set x2 and x4 to 0, we are left with this system here. And from this, we can read off the solution. So x3 has to be 1, and if x3 is 1, x1 is going to be 3. So the basic solution determined by B is 3, 0, 1, 0. And this is a feasible solution to P, and so B determines a basic feasible solution. So that checks the first condition. Now let's look at the second condition. So we need to solve this system of equations. This system looks like this. So y1 star, y2 star times the submatrix of A consisting of the columns indexed by the elements of B. And the right-hand side will be 1, 0. So expanding the left-hand side, we get y1 star in the first entry and minus y1 star plus y2 star in the second entry, and that equals 1, 0. So y1 star is 1, and if y1 star is 1, this tells us that y2 star is also 1. So once we have this, we need to check these conditions. So when J is 2, this product equals 1, 1 times 2, 1, and that's equal to 3. And 3 happens to be the same as the second entry of C, so that's fine. And when J is 4, we are looking at this product here, and 1, 1 times 1 minus 3 is minus 2, and minus 2 is less than minus 1, so again, that's fine. So all these inequalities are satisfied, and so the second condition is also satisfied, and we can conclude that B is an optimal basis. So now let's look at our second question. So we are now changing two entries of C, the first one to theta and the second one to gamma, and we want to see what are the conditions on theta and gamma so that B is still an optimal basis. As before, we need to check two conditions. The first is that B determines a basic feasible solution. But if you look here, if we are changing C, this system here is not changed. So we can use the information from the previous question and conclude that B is a feasible basis, that is, it still determines a basic feasible solution. So what we need to check is the second condition, that Y star satisfying this implies that Y star transpose A2 is at most gamma, and Y star transpose A4 is at most -1. So we need to solve for y star first, and this system is simply y1 star y2 star times 1 minus 1, 0, 1 equals theta 0. And if we multiply out the left hand side, we get y1 star in the first entry and minus y1 star plus y2 star in the second entry, and that is equal to theta 0. And here we see that y1 star has to be theta, and the second entry tells us that y2 star has to be equal to y1 star. So the solution is y1 star equals y2 star equals theta. Now we need to plug this into the left hand side of these inequalities and obtain conditions on theta and gamma. So this is true if and only if theta times the second column of A, which is 2, 1, is at most gamma, and the second inequality reads theta times the fourth column of A, which is 1 minus 3, is less than or equal to -1. And this is the same as saying 3 theta has to be at most gamma, and -2 theta is at most -1. And we can combine these to obtain a succinct condition on theta and gamma. So from the second one, we see that theta has to be at least a half, and from the first inequality, we get theta is at most gamma over 3. So B remains an optimal basis if and only if theta and gamma satisfy these inequalities.